For this problem, you're told that the table shows time to speed data for a car accelerating from rest to 120 miles per hour. And then it says how far had the car traveled by the time it reached this speed. Use trapezoids to estimate the area under the velocity curve. Now, I went ahead and I graphed the data from the table. So notice that the x values represent the time in seconds, and the y values are going to represent the speed, but in the graph, the speed's in miles per hour, and that's where we're going to have to make a change here because we're working in different units. Time is in seconds, speed is in miles per hour, so we are going to need to do some conversions, but I'm getting a little bit ahead of myself. So what I've done is I've graphed the data at time 0, the speed is 0. At 2.2 seconds, the speed is at 20 miles per hour. 3.4 seconds, it's at 30 miles per hour, and it continues. Now, what we're going to do here is create a whole bunch. It's going to be, I think, 11 total trapezoids, and estimate the area under that velocity curve with those trapezoids. Because the velocity function is the derivative of the distance function, finding the area under the curve is going to give us the distance. And again, we're going to use trapezoids. So you could imagine, and this is probably not going to look really pretty, but imagine if you were to drop, oops, let's see if this will work. There we go. If you were to drop verticals down from each of these points, you would be creating the different trapezoids. And you could do that all the way across. I'm not going to, but you could do that all the way across. And then you would have 11 different, if I'm adding 1, 2, 3, 4, 6, 7, 8, 9, 10, yes, you'd have 11 different trapezoids. And you can see at the end, your trapezoids get wider. So if you look at the very last trapezoid, it's much wider than the first. So we can't use the trapezoidal rule with the change in x values being constant. Here we're going to have to find the areas of these individual trapezoids and then add them together. Before we can do that, though, we need to make sure that our units are the same. The question asks for the answer to be in feet. Since the time is in seconds, what I need to do is change all of these speeds from miles per hour to feet per second. And I have a table here where I have done that. It's not terribly difficult to do that. Let me give you for instance, at 8 seconds, the speed was 60 miles per hour, and you can see it's 88 feet per second. So what you would do is take 60 miles per hour. In a mile, you have 5,280 feet. So that would cancel my miles out. And then an hour is 3,600 seconds. So this now gives me speed in feet per second. So to get that answer, it's 60 times 5,280, then divided by 3,600, and that gives me my 88 feet per second. So you would do this process for each of the different speeds. The 5,280, the 3,600 aren't going to change, of course, but you would just change out your initial miles per hour speed. So that's where I've got this second table. So I have the time listed and then the corresponding speed in feet per second. Now, what I need to do with that information is find the areas of these different trapezoids. To find the area of a trapezoid, and all of our trapezoids are going to take this basic shape. You're going to take your change in your x values, which I'm going to call delta x, and then you're going to average the two y values that make up the left and right sides of that trapezoid, average those together, multiply by that change in x values. That gives you the area of a trapezoid. That just goes back to basic geometry. So we're going to do that for each of these little trapezoids that are created. So I have a table here. It's a lot of just tedious calculator math. So there's a total of 11 trapezoids. So in my table, you'll see there's all 11 trapezoids. So the first one is this one that's really more of a triangle than a trapezoid. The delta x, it goes from 0 to 2.2 seconds. So you can see I took 2.2 minus 0, so my delta x is just 2.2. And then I average the length of those two sides. So the first speed, that's what the two sides represent. The first speed was 0. The second one was 29.33333 feet per second. Average those together, you get your answer. To find the area of the trapezoid, you multiply your delta x by that average of the length of the two vertical sides. So the area of that first trapezoid, 32.266663. And you want to make sure you leave lots of decimal places. My math lab, I was playing around with it. It's very particular on this one. It wants it exact to the thousandth. So you're going to repeat this process for all 11 trapezoids. So for the second one, you're looking at 3.4 minus 2.2 for that change in time. So it's 1.2 seconds. You're going to average the two speeds, and that's here. Multiply together the area of that trapezoid, 43.999998. So you're going to do that all the way down. And you can see, and this should make sense. Let me come back up here to the graph. The trapezoids are getting bigger as more time passes, so you can see the areas are getting larger. Once you have all of the areas, to find the total distance traveled, it's the total area under the curve. So you're going to add up all of the individual areas of those trapezoids, and you end up with 4,843.667 feet. So this one is a lot of tedious calculator work, unfortunately, but hopefully this makes sense. I wasn't sure exactly what part of the process was the most confusing for you, and it might have been something as small as just making the conversions up here. But hopefully this helps. If you have any questions, just let me know. Thanks.